All right, today we will be taking notes on graph theory. There's a in-class handout on Canvas, so make sure you have that ready to go. After we do the notes, I'll give you some time to work on that in groups. So let's talk about graph theory. This is probably new, kind of uncharted territory for most of you. This is not really something that's covered in high school math classes, whether it's algebra or trigonometry or geometry. This is kind of its own branch of mathematics that is useful for answering kind of real world questions, but you don't really see the applications until you start digging into graph theory specifically. The word graph here is not necessarily like the XY axes. It's more about vertices and edges connecting those vertices. So we're going to define what a graph is here, which is, like I said, not like when we graph a function, but this is more about a visual representation of vertices and edges. So things we study in geometry are kind of a subset of graphs. Graphs will be defined as a collection of vertices and edges. So a graph is defined as just a collection. There's a visual representation of graphs, which you may have seen in the video, but as sets, we'll talk about a couple of different representations. As sets, we'll write a graph as a set of vertices and a set of edges. We'll call the set of vertices V, and this set will have letters for the vertices of the graph. So A, B, C, D, and E. This is just an example of a graph. Obviously, if you have more vertices, then you have more elements in your set. If you have less, you have less. And then we'll write the set of edges, which will be written as ordered pairs of these vertices. So, and an individual edge would be something like A comma C. So each thing in here, each tuple is going to be a ordered pair that is an ordered pair of vertices, which means there's an edge between those two vertices. So I'll write a few of these here. AC is one of them. BD is going to be another one. EA, CD. I'm just writing this as an example. This is not coming from anything. AB. So you have an example of a graph. D comma D can be another edge. And then we'll do one more. We'll say A comma E. So, as sets, this is how we can write a graph. So this, right here in the box, is a graph for all intents and purposes, right? So if you see this, that is an example of a graph. Now we can take that set representation of a graph and we can convert it into a diagram. So as a diagram, we can kind of represent the same set as we've done in this example up here as a diagram. And we'll have to just make vertices and then connect them using the edge set that we're given here. So I know that there's going to be 5 vertices labeled A, B, C, D, and E. So I will do that. So I will just make 5 dots, and the orientation or the sequencing of the dots is not significant. You can draw this however you want, but generally it's nice to space them out in a way where if I draw an edge between 2 of these vertices, it's not going to be confused for another edge. And the vertices are kind of spaced out. Like I said, you can draw this however you want, but you should have 5 vertices, and then the set of edges are going to be represented with lines connecting these vertices. So the first edge I have here in my edge set is A comma C, which means there is an edge between A and C. Right? The next edge is B comma D, which means there's an edge between B and D. Next edge is E comma A, which means there's an edge between E and A, connecting E to A. Next one is CD, so I have an edge connecting C and D. Next one is AB, which means we have an edge between A and B. DD is an interesting one. That is what we call a self loop, which means there's an edge connecting D to D, and we'll represent that with some kind of loop connecting D to itself. Because it doesn't have to necessarily go around the letter D, but there's an edge that connects D to itself. And then finally, AE means there's an edge between A and E, but I already have one there. But the fact that there are two edges connecting A and E in this set means there are two edges connecting A and E in the diagram. Again, notation-wise, this is called a loop in the diagram on D, and these edges here, where I have two edges connecting A and E, are called parallel edges. Right, so some terminology there. Parallel edges and loop is what we've defined there. Right, so terminology-wise, we have things called degree. The degree of A, we'll talk about. The degree of E is an interesting one to look at, and then degree of D is another interesting one. Degree is essentially the number of edges that are connected to a vertex. So if I look at vertex A, the degree of A is going to be how many edges are coming out of vertex A. And the best way to think about this so that there's no confusion with this loop business is to kind of draw a really small circle around vertex A and see how many edges intersect that circle. So if I zoom in real close to A and I look at this little circle here, this window here, how many edges do I have hitting that circle? And the answer there is 4. So the degree of A is 4. All right, so degree is how many edges, how many directions can I leave out of A, essentially. If I'm a little dot traveling along these edges, how many ways can I leave A? And there's 1, 2, 3, 4 ways to leave or enter A. If we look at E, if I look at a really small circle around E, there are 2 edges that we can leave from E or enter into E. So the degree of E would be 2. Now the degree business gets a little bit weird when you introduce this idea of a loop. Because if I said how many edges are touching D, you may say, okay, there's one edge, there's another edge, and then this is the third edge. But in fact, if you do what I said and you draw a little circle around D, there are 1, 2, 3, 4 ways out of D or into D, right? As if we think about it in terms of traveling along the edges. So the degree of D is also 4 because there are 4 ways in and out of vertex D. Right, so it's not necessarily the number of edges that are touching D, it's the number of edges leaving, or the number of ways to leave or enter vertex D. So if I define, if I give you a definition for degree down here, degree of a vertex, that is the number of edges. I don't want to say edges because that gets confusing. We can define it as the number of paths in/out of a vertex. We'll define a couple more things here. We'll define what a simple graph is. A simple graph is defined as a graph with no loops nor parallel edges. So my graph up here, the one I've given as an example, is not a simple graph because we have a loop and we also have parallel edges. So a simple graph would have none of these and no parallel edges. There would only be one edge connecting any two vertices, and there would never be a self loop connecting a vertex to itself. That's what a simple graph is. Next, we're going to define what an Euler circuit is. It's written like Euler, but it's pronounced Euler. Circuit. An Euler circuit in general, or a circuit in general, is kind of a path around a graph that starts and ends at the same vertex. So that's what a circuit is. Specifically, an Euler circuit is a circuit that uses every edge exactly once. An Euler circuit will start and end at the same vertex and will use every edge exactly once. It's essentially a path around the graph from vertex to other vertices using edges, where you can go around the whole graph and you will use every edge exactly once, and you start and end at the same vertex. For example, if I were to try to draw an Euler circuit on this graph, I could start at pretty much any vertex here. Let's say we start at vertex B, and we want to travel around the whole graph, but we want to use every edge exactly once. We could do something like use this edge along, you go along this edge to go to A, and then go to E, and then back to A, and then to C, and then to D, and then take the loop around D, and then go back to B. The key is here that I've used every edge exactly once, and I've started and ended at the same vertex B. Notice how it doesn't say anything about using or going through vertices multiple times. That's allowed in an Euler circuit. The only thing that is not allowed is using an edge multiple times. Right? So we use every edge exactly once, and every edge must be used, and you have to start and end at the same vertex. So because I found one starting at B and going around the figure, using every edge exactly once, never repeating any edges, we can answer the question for this one here and answer the question of does this graph have an Euler circuit? Question mark. And our answer to that is yes. And we can write the Euler circuit by writing the edges in the order that, the vertices in the order that we visit them. So if I'm going to start my circuit at vertex B, so if I'm going to write down the sequence that I had, I would say B to A, and then I went to E, and then back to A, and then to C, to D, and then I took the self loop on D, and then I ended up back at B. So as long as you have a sequence of vertices that are visited, starting at a vertex, ending at the same vertex, and along this path, no edge was used more than once, then this is an example of how to represent an Euler circuit. So we can write it as kind of just the path that you follow and the edges that you take. So you go from B to A first, which is this edge, obviously, and then A to E, there's a choice there. You can either go this way or this way. Doesn't really matter because we're coming back from E to A on the next step. So we go A to E and then back to A, and then we go to C, and then to D, and then back to D itself. That must be the self loop, and then we end up back at B. So this is an example of how we would write an Euler circuit. Any questions so far on terminology? Okay, so if we understand the terminology, I just kind of started at B and kind of just went in any direction and hopefully made an Euler circuit. There's got to be a way of knowing whether or not an Euler circuit exists, and then a way of writing it that is kind of algorithmic, right? There's got to be a way to know whether or not looking at a graph there is an Euler circuit. Because what if I went the other way from B? What if I didn't start at B? What if I start at A? There's 4 different ways to start if I start at A, right? So there's got to be kind of a formulaic way of knowing whether or not there is an Euler circuit, and then also writing it out. Which is where the next thing is going to come in, which is going to be a theorem about Euler circuits. So the theorem for Euler circuits is that a connected graph, connected just means that there's only one piece to the graph. A disconnected graph would be like if you had a graph with one piece and then a separate piece over here. If you had a graph like this, that's not considered a connected graph because there are 2 separate pieces where you cannot get from one piece to the other and there's no edge connecting them, right? So a graph has to be connected in the first place to even have an Euler circuit, because you obviously can't go to every vertex and use every edge if you can't get from one piece to another. So a connected graph has an Euler circuit if every vertex has an even degree. So we talked about what the degree of a vertex is earlier, and the requirements for having an Euler circuit. So the answer to this question, does this graph have an Euler circuit, can be answered by just looking at the degree of every vertex and seeing if they're all even. All right, so to answer this question, we said yes because we found one, but we can also say yes by looking at the degree of all of these vertices. And I'm actually going to write the degree of each vertex next to each vertex, which is something we should do whenever we're looking at a graph. So when I look at vertex E, the degree of vertex E is going to be 2. So I'll put a little 2 next to my vertex here. Sorry. I'll put a little 2 here next to that vertex. Vertex A has degree of 4. We already answered that question, so I'll put a little 4 next to that vertex. B has 2 edges that are coming out of it. C has 2 paths coming out of it. And we already answered that D had a degree of 4. So if I look at all of these numbers, 2, 4, 2, 2, 4, I can answer the question, does this graph have an Euler circuit? with the question, are all of these numbers even numbers? And the answer being yes there means the answer to the does this graph have an Euler circuit is also yes. And as a heads up, if the answer is yes to the Euler circuit, you can actually start at any vertex and end at the same vertex, as long as you're kind of careful with the way you go around, right? So if I wanted to start at E and end at E, I don't want to go E to A and then go back to E, because that would end my circuit without visiting or without going over every edge. So if I wanted to start at E, I would need to go to A, and then we can kind of go in any direction from there, as long as we don't go back to E until we've taken all of the edges, right? So go to A, I can go to B from there, I can go to D, I can go around D, and then go to C, and then go to A, and then and then finally go back to E. Sorry. So there's a few ways you can do it. If I go to A first, I can go to C, and then to D, and then go around D, and then back to B, A, and E. So there's many different ways of writing an Euler circuit. As long as you cover every edge in your circuit, then you've essentially described an Euler circuit. Right? But if the answer is yes to an Euler circuit, you can start at any of these vertices and make an Euler circuit. Okay, next thing we're going to define is an Euler trail. So let me actually put a box around these, because these are kind of together with the definition of an Euler circuit and the theorem for when there is an Euler circuit. And then we'll do the same thing for an Euler trail. We'll define what it is, and then we'll have a theorem for when there is and when there isn't an Euler trail. Euler trail, it kind of follows the same naming scheme as an Euler circuit. So Euler essentially was concerned with using every edge exactly once. So an Euler trail also uses every edge exactly once. But the difference here is in the word trail, and I'll tell you what a trail is right now. So an Euler trail will use every edge exactly once, but what a trail is that it will start and end at different vertices. So the difference there is the circuit has to be a closed loop, essentially, ending at the same vertex that you started at, whereas a trail is going to start at one vertex, go around and collect every edge, and end at a different vertex. And I'll just give you the theorem for a trail as well. A connected graph has an Euler trail if there are exactly two vertices with odd degree. So exactly two vertices with odd degrees, the requirement there. Remember, the requirement for an Euler circuit was every vertex had to be even. So as soon as you have exactly two vertices with odd degree, and everything else obviously is even, you have an Euler trail. So this is goes with I want to add a note to this. We'll put a little star here and say that the Euler trail will start and end at these two odd degree vertices. So the fact that there are exactly two vertices that have an odd degree is significant because that's where we have to start and end. Those two vertices are where we would start and end the trail that we're looking for, right? So it gives you a starting point and a goal for the ending point for the trail. All right, so we have our definition for a trail and a theorem for when there is one and there isn't one. So if I go back to my example here, this example obviously has an Euler circuit, so it cannot have an Euler trail because to be a circuit, to have a circuit, they all have to be even degrees. And so if all of the vertices have an even degree, then there's no way that you have exactly two with odd degrees. But if there was a new edge introduced to this, I don't know if I want to mess up the notes. But you can imagine if there was an edge connecting E to B, for example, then these numbers would no longer be 2 because E now has a degree of 3 and B has a degree of 3. And A, C, and D are unchanged, which means there are exactly two odd vertices in that situation. And the answer for the Euler trail would be yes. And any Euler trail you write like this would have to start at E and end at B, or vice versa. You'd have to start your trail at B and end at E, or start at E and end at B, while also going over every edge exactly once. Right, so for an Euler trail, you're looking for exactly two odd vertices to guarantee that there is one. For a circuit, you're looking for all vertices to have an even degree.